Hey everybody, Mr. Mac here, and let's do some work. I'm going to look at the notes for 1.3 radicals and rational exponents. Here we have a radical expression. This square root symbol is our radical, and inside the radical or underneath the radical, we call the number here the radicand. And so the principal square root for a non-negative number a can be written like this: square root of a, radical symbol over the radicand a. And the principal square root is going to be a non-negative number. So in other words, positive. Okay? We see when we solve equations that have square roots, we often get a positive and negative answer, but the principal square root of an expression is always going to be positive. Okay, so let's have a look at, what do I want to do now? Yep, let's jump right into evaluating some square roots here. So square root of 100, well, I hope we see that's a perfect square. So another way to write this is 10 squared square rooted, and the square root and the square would cancel, and so this would leave us with 10. So that's my solution there. Maybe I'll start boxing these in again. Okay, and the next one, we have the square root of 16. So we always want to start on the inside and work our way out. So the square root of 16, you know, if I wanted to rewrite this, I could say 4 squared is the same as 16. And the square root and the square symbol would cancel. So this would be 4. And of course, the square root of 4 is 2. Hope this is working for you guys. Start off with some things that you know, hopefully. Get some confidence. Square root of 25 plus 144. So we are always going to follow the order of operations. And I think my marker here, or my stylus, is too thick. Let's bring that down a little bit. And so we have underneath the radical here, we've got 25 plus 144, which is our radicand, right? And even though we don't see it, we know that this quantity right here, we could write in parentheses like that. And so we would want to do everything in the parentheses first. So let's not take the square root of 25 and 144 separately. We must add these things first because it's in the parentheses here. So you would think that, oh, we do the exponent and the radical first and then we add or subtract, but this is considered to be in parentheses. So the square root of 25 plus 144, that is 169. And 169 is a perfect square. I could rewrite it like this if I wanted. I could say 13 squared is the same as 169, and the square root of a square cancels, so my answer would be 13 for this. That's my solution. And let's select the pay bucket. There we go. Okay, on this one right here, we've got the square root of 49 minus the square root of 81. These are separate expressions here, so 7 minus 9 is negative 2. Okay, moving along. So the product rule for simplifying. There's a lot of ways to simplify, and I'll explain some alternatives. But we could say, you know, A and B are non-negative numbers or variables. The square root of a times b, so ab is the radicand right here, a times b equals the square root of a times the square root of b. So we can separate these, and this is the product rule. So we already saw, let's use that for, let's think about how we can use this rule here in these problems, right? So we already saw that the square root of 100 is 10. We just did that above. So we could rewrite this as the square root of 100 times the square root of 3. 100 times 3 is 300. So we're using this rule right here exactly, and we know the square root of 100 is 10, so I could say 10, and square root of 3 doesn't simplify, and we'll just leave it under the radical. So that's my solution for A. Okay. Now let's see if we can use the same rule for this problem. So 162, I'm just going to factor out a 2 here from 162, and I get 81. Now we know 81, hopefully, right here. We know this is a perfect square. And so we could rewrite this 162 part. We could say, okay, this is root 81, and we could say times root 2, right? So I just did the coefficient here. What about a to the 5th? So we could take out a to the 4th here, because a to the 4th is a perfect square, and also b to the 4th. Running out of room here, making it tight. So that means I would have an a square root of a over here. So 81 times 2 is 162. A to the 4th times a is a to the 5th, and b to the 4th is right there. And I can simplify all of these right here. So this would be 9, a to the 2nd, b to the 2nd. And then right here, I've got root 2 and root a. I can just put those back together like that. And that is my solution. Okay, that's using the product rule of radicals to simplify. Okay. Use the product rule to simplify the product of multiple square roots. Okay. Again, there's a couple different ways of doing this. The way that we can put this back together, sort of undo it, right? 12 times 3 is 36. So I could rewrite this as the square root of 36. And we know 36 is a perfect square. So my answer would be 6. And that's simply all we do. Okay, so sometimes we break it up to help us simplify. In this case, I put it back together. Quotient. Quotient rule, quotient, fancy word for divide. Not fancy, but mathematical. The square root of the quotient a divided by b is equal to the quotient of the square roots a and b, where b is not 0. Well, we can't have b be 0 here because that would be dividing 0, and we can't do that. So the idea here with this is if we have the square root of this fraction, we can just separate the radical here, the square root, in the numerator and the denominator. Like this, and then we'd say, oh, the square root of 36. I know what that is. That is 6. And that's all we do. Okay. You know, I think you can see the square root of 36 in the bottom and just write 6, but you know, we are thinking that the numerator can be broken up from the denominator to help us see the simplification. Okay, so example 5. Our radicands here are a little more interesting. Use the quotient rule to simplify an expression with 2 square roots. Okay, so we have 2 square roots. Maybe, so we could try to pull out perfect squares here. You know, they're inside here for the x for sure, right? And down here. And Maybe 234, we can look at factoring in that. But the idea for this one is, hey, let's just put it all under one big square root. And then let's simplify from there. Yeah, look at the y's, for instance, right? They're going to cancel. And a lot of the x's are going to cancel. So we're going to get something like this. Okay, so 234 and 26. Does 26 go into 234? Let's try it. 234 divided by 26. I got my calculator here. It's 9. Oh, well, that's very nice. Maybe I'll write it up here. So 9, love 9. 9's perfect square. And how about I do this? You know, we can use the quotient rule here for our exponents. 11 minus 7, right? That's from last section or so. And then, you know, we got 1 minus 1 here. And so we're going to get, you know, I'm doing a lot of extra steps here that you guys, just trying to be completely explicit here in my thinking. I'm going to write it all out. So what's the square root of 9? 3. Square root of x to the 4th, x to the 2nd. Remember what happens when we raise something to the 0? It gives us 1. So that's it. There's our final answer. Okay. Moving on. Adding square roots. Okay, adding square roots. So it's really important whenever we add square roots that the radical and the radicand have to be the same. Okay, so the number inside underneath the radical has to be the same. And you know, these are both square roots, but we could have cube roots and things like that. So it's got to be the same radical. So 12 and 3 are not the same. So do we just give up and say, oh, we can't add these? Well, 12 has a perfect square factor in there. So how about we rewrite this as 4 times 3. Square root of 4 is 2. So I'll be completely explicit here. That 2 comes out there, and the 3 is still here. Okay, that 2 is right here now. Square root of 4 is 2. And this is all being multiplied. So that's going to be 10 root 3. So if I have 10 root 3's and I add 2 root 3's, I put all my root 3's together, I have 12 root 3. You know, it's like if I had 10 oranges and 2 oranges and I put them together, I have 12 oranges. Well, this time these are root 3's. I put them together and that's what I got. Like terms are these radicals. That's why we can add those. 12 root 3. Okay, example 7. Subtracting square roots. All right. Same deal. We can't just say 20 minus 14 is 6, and then what would the radical be, right? So the radical, the radicands, the radicals, they have to be the same. So what can we do here? So 72, I know if I just do a little factor tree here, 2, I know 2 goes in because it's even, and 36. Okay, 36. I know something about 36. It's a perfect square. Okay, I have a cubed here. Well, what if I take out an a to the 2nd, and I have b to the 4th? Okay, these are all my perfect squares. I'm just putting them out right here. Times, now what's left here? I still have a 2. Still have a 2 in there, the 72, right? I have an a left over. And that b, all the b's came out, but there's a c, there's an odd c right there. Okay, so this expression is done, minus 14. Okay, 8. You know, 8, if we take a 2 out of 8, factor 2 out, I get 4. So I shouldn't have put that there. That's in my way. I'm going to erase that. So that means I could take a 4 out. I have an a to the second. I have a b to the fourth. These are all perfect squares here. That c cannot come out. So what's left in here? I got a 2 still left over. I have an a and a c. All right, there's that extra a from here. All right, so let's simplify this. 20 times 6, a, b to the second, root 2ac, minus 14 times, okay, I got a 2, I got an a, b to the second, and then 2ac. All right, so 20 times 6 is 120. 120, a, b to the second, 2ac. 14 times 2 is 28. A, b to the second, 2ac. Okay, so now notice here is my expression here. AB to the second, root 2ac, and then right here, AB to the second, root 2ac. These are like terms. These terms have all the same variables and values on their exponents, radicals, radicand, all that. I have 120 of these and I'm taking away 28. So if I take 28 away from 120, that would be what, 92? 92 AB squared root 2AC. Boom. That one's done. This is example 7. Very good. Rationalizing. Notice we've got the word ratio in this rationalizing word. Ratio talks about fractions. We do not like having radicals in the denominator. That's just considered not simplified when we do that. So we don't want the radical in there, and it says denominator containing a single term. Okay, so the way we get rid of radicals is by multiplying them times themselves. So let's think here. Let's say, I'm just going to make up one real quick here. Let's say we have root 3, and I want to get rid of this radical. Let's say we even have 1 over root 3. What can I multiply to get rid of this radical? Well, if I multiply it times itself, that would give me the square root of 9, and the square root of 9 is 3. So that gets rid of the radical. But in order to make this a legal move here in math, whatever we multiply on the bottom, we have to do to the top. So my answer here would be root 3 over square root of 3 times square root of 3 is 9, and square root of 9 is 3. See how I got rid of it right there? So we're going to do that same move right here. We're going to multiply by root 10, top and bottom. Now, this gives me 2 times root 30. Okay, we just use that rule, putting these together, over 3. Now I could write this out, right? Root 10 times root 10 is root 100, right? Root 100. But what is the square root of 100? Is 10. So I'm going to write 3 times 10. And now, let's see here. I could put these together. But look, 2 and a 10, I know I could take a 2 out of 10. That would give me 5. So I just simplify. That's 2/10 right there. That would be 1/5. And my final answer is root 30 over 3 times 5. All right, everybody, I'm going to stop there to split this video up, and I will do the next set of examples on another video. So see you then. Later.